European lectures online, and it's really great to see everybody here. My name is Erik Offerman. I work at Delft University of Technology, and I would also like to welcome you on behalf of Annika Borgenstam and Joachim Ottqvist from KTH in Sweden, on behalf of Leo Kestens from Ghent University, and of course my colleagues from Delft, Maria Santofimia and Jo Zietsma. Yeah, and we thought that it would be maybe a nice idea to get together as experts in metallic microstructures, and yeah, in these times get connected again, and also to be inspired. And that may not be so easy in these times, but I think with a series of European lectures, we can do that very well, and I'm very much looking forward to it. And I'm also very happy that yeah, so many people are already online, and yeah, apparently also feel the need to get connected and be inspired by our colleagues. Yeah, we organize this we will organize this every third Thursday of the month. So the next meeting is already on the 20th of May. And Baptiste Gould from the Max Planck Institute will present about atom probe tomography then. So you can already put it in your diaries. Furthermore, it's maybe good to know that, as you can see already in the top left of your screen, that this is recorded. And this is to say that only the presentation of our first speaker, Ernst Kozeschnik, will be recorded. We will not record the discussion. So it's only the presentation. And Professor Bedesha was so kind to offer the recordings afterwards on his YouTube channel. So in case there are colleagues who cannot follow today's lecture and would still like to see it, there will be a possibility in the very near future. I don't know the details yet, but we'll make sure we communicate that to you as well. Yeah, then maybe it's also good to know that you can ask questions, but do that after the presentation. So I would prefer not to type questions in the chat during the presentation. At least I find that distracting. Of course, you can already prepare your questions in the chat, but wait with pressing send until the end of the presentation of Ernst. Of course, after the presentation, you can also ask your questions just by microphone and by video, but also by chat. So I will go through the chat as well to see which questions popped up. Okay, I think that as far as the organization is concerned, and I hope I have not forgotten anything, then I would like to say that I'm honored and very pleased to introduce the first speaker of this series of lectures, Ernst Kozeschnik. I'm very happy that you dared to be the first speaker of this online format. It's really great to have you here. Yeah, I think you don't require much introduction. You're an excellent scientist. You're the driving force behind MetCalc. We have seen you organize a Thermec conference, of which I remember a very pleasant conference dinner. But even in COVID times, you are also organizing Thermec, trying to get people together in the field. And yeah, that's obviously very much appreciated. And we're very much looking forward to your presentation about nucleation in polycrystalline metallic structures, classical theory, and recent extensions. The floor is yours.
Okay, thank you. Erik, a very nice introduction. I'm not really doing too many things in the Thermec organization, by the way. So that is in very good hands from Tara Chandra and Mikhail. So now that should be visible for you, I guess.
Maybe it's good to mention one thing that I forgot. If only Ernst is on the camera. If you don't want to be on the video, so to say, to re-record it, then you have to switch off your camera because some people will still be visible. So, of course, Ernst, please keep it on.
Okay. I have a little bit for everybody. So everyone who is new in nucleation will learn a little bit about classical nucleation theory, and the other ones will learn a little bit about yeah, what my group is doing or what we are doing at the moment. In fact, when Eric's email came into my mailbox asking me for the first presentation, I went like, oof, I have no time. But in fact, I was working on a paper on some extension of theory, and it came to my mind that, yeah, why not give you a little bit of insight into what we are thinking nucleation occurs, and you will immediately recognize when the references that I give on the pages on the slides will switch to unpublished research. That will be exactly the paper that I was working on when the invitation came for this presentation. So I will talk a little bit about classical nucleation theory, and then discuss all the extensions that we have developed in the last years. And I will show you two examples in the end where I think the agglomerate of all these ingredients is needed to describe two kinds of experiments. The one is solving the question of what the chemical composition of a nucleus could be in the optimum case, and the other one will be a continuous cooling DSC experiment where I just couldn't get the simulations and experiments in line unless we extended theory a little bit. I'll try to make it in 1 minute. TU Wien is the capital of Austria. We are in the middle, in the center. That will be a topic center of Europe. We are on the edge of Austria, but we are in the middle of Vienna. So this is a map of Vienna. You see the red mark is Technische Universität. And when you look at this center here, this is St. Stephen's Cathedral, and this is TU Wien. So we are pretty much in the center of Vienna, which is very nice for students because you have a lot of places where you can distract yourself a little bit. We have roughly 5,000 personnel and 26,000 students. We are the largest TU, technical university in Austria. And the institute where I come from is the one for material science and technology. We have seven research groups. We can see one group working with thin films, one with polymers and additive manufacturing. And the one where I'm in is metallurgical process engineering. So just to give you a very rough overview where I come from and what my colleagues are. Yeah, when we talk about classical nucleation theory, we are talking about a phenomenon where you have some solution, like a cloud, like the water molecules in the cloud. And under certain conditions, these molecules will form aggregates that precipitate out of the cloud, which is exactly what also happens in metallic microstructures. I will show you a few differences later on, but basically the process of rainfall and precipitation of nucleation of second phases is very much comparable. When you look at some kind of, let's say, solution, then you will recognize that the monomers or the molecules that will form the second phase appears either as a single molecule or together with like dimers or trimers and so on. And eventually, when you have a supersaturated solution, there might come up a nucleus which is large enough to become stable. And the main idea of classical nucleation theory is now to consider this nucleation event in terms of the local energy, the changes in the bulk energy, the volume energy, and the changes in the energy related to the creation of new surface. So we have a term which involves the volume free energy change due to the change of phase multiplied with the volume of the nucleus, and the same with the specific interface energy multiplied with surface area. So when you put these ingredients together, you can write down the nucleation energy. And it's well known, we have the interfacial component scaling with the square of the radius of the droplet or the particle, and the volume energy with the cube of the radius. And that will lead to the observation of a barrier. And the barrier can be very easily evaluated in terms of the extremum value. So you take the nucleation energy, first derivative equals to 0, and then you get the critical radius and the critical energy nucleation barrier. And this nucleation barrier is an extremely central quantity because the nucleation barrier, the shape of the nucleation barrier will allow us to formulate nucleation rates for new particles. So keep in mind, nucleation barrier is a very, very central quantity. And the barrier contains more or less two parts. The one is the interfacial energy cubed and the volume free energy change, or let's say that the driving force for second phase formation squared. Yeah, so these two quantities are more or less the ones that we are interested in the further study, because one of my favorite things is always predict something and do not simply fit to something. Yeah? So my ambition has been to predict nucleation of new phases instead of just fitting quantities like interface energy is a typical quantity. I don't want to fit that, I want to predict it. So this is classical nucleation theory. The idea is to define this nucleation barrier from the volume and the surface contributions. The talk here is about metallic microstructures. And the metallic microstructure is usually one which is crystalline. And in contrast to raindrops that form in a cloud, we have some limitations here in the solid state case, and that is related to the crystal structure. And I've plotted like a precipitate on the left side, which is coherent with the matrix. The precipitate is the dark balls. And on the right side, I have plotted the case where the precipitate contains atoms that are larger in volume compared to the surrounding matrix. And in that case, and that is very typical for solid state precipitation or nucleation reactions, we have some elastic energy. The stress field always acts against the nucleation process. It can be easily evaluated, this elastic modulus Poisson ratio, and this epsilon star is the linear misfit of precipitate and matrix. It doesn't matter whether it's larger or smaller because we have the cube here and the energy is always a positive value. And that will always act against nucleation. And I think in most cases, you definitely have to take these elastic stresses always into account, because I think most nucleation processes are more or less occurring in coherent structure. Yeah, nucleation theory should be extended. The critical quantities are now adding also up the stress energy. Yeah, and you can see it's got the different sign compared to the chemical driving force. So it's always reducing the chemical driving force and actually increasing the nucleation barrier, because this is below the fraction. Another feature when you look into metallic microstructure and when you look at precipitates is that these new phases strongly interact with heterogeneous sites. So this is a carbon extraction replica and a bright field image from martensitic steel with lots of precipitates, and you can see that those are very usually very commonly oriented along subgrain boundaries. Dislocations could be a very prominent heterogeneous nucleation site or grain boundaries. So this is something that we also should take into account once we discuss nucleation in polycrystalline structures. And just a suggestion how we take that into account in our simulations, we model the grains as tetracade decahedrons, which are space-filling objects. And the advantage of that is it's very easy to define, let's say, a grain size. And from that, you can very easily calculate the volume of the grain, the area of surface of the grain. You can easily calculate the length of the grain boundary edges and also count the grain boundary corners. Now, when you take that into account and when you think about nucleation always occurring on heterogeneous sites, then you can define the number of possible positions in your microstructure very easily. And this is a table which I was calculating many years ago, where you could see, for instance, if you consider that every atom in 1 cubic meter of material is a potential nucleation site, then you can see that for homogeneous nucleation, you have roughly 10 to the power of 29 sites. If dislocations are favored nucleation sites, then we are orders of magnitude smaller already, depending on how many dislocations are available. Grain boundaries, of course, very much dependent on the grain size. The subgrain boundaries, if you have elongated martensitic grains, and if just grain boundary corners are favorite sites, you can see that the number of possible sites is decreased by many orders of magnitude. And just to give you an example, grain boundary corners will be very prominent nucleation sites if you form ferrite from an austenitic matrix. So when austenite decomposes into ferrite, many times the grain boundary corners will be the prominent sites. So the metallic microstructure will definitely impact nucleation of particles by simply providing a various number of potential nucleation sites. Yeah, let's go on a little bit with classical theory and have a look where these solid state features come into play in the nucleation rate expression. The classical nucleation rate expression is the one which is on the screen. I have added two references where one can look for the source of this equation. So the first one is the Seldovich, the classical paper from Seldovich from 1943, who actually more or less develops exactly this equation. When you look into the famous paper of Kenneth Russell, you will find that that he claims that there's no real derivation, and he just writes down this equation. So you can see it either way, either developed on a rigorous basis or just yeah, and a little bit of phenomenology in this equation. So what are the ingredients of this? Have a look at the exponential term. This is the most important one. The exponential term contains the nucleation barrier, G star. And that will already indicate that G star is a very, very, very important quantity, because the exponent of G star is a term that changes by orders of magnitude if you change the G star just by a little bit. I will show examples later. And the three terms, the pre-exponential factors, N, Z, and beta star, they are more or less related to, a little bit also the thermodynamics, the kinetics, and the microstructure. For instance, the N0 is the number of potential nucleation sites. And you just keep in mind that I was showing you this tetrachedecahedron and the different numbers in the table. So this is exactly where the microstructure enters in terms of the available sites. The Seldovich factor Z is thermodynamic, and it's actually related to the second derivative of the nucleation energy at the barrier, so at the critical point. So if you go into more details of nucleation theory, you will find that the vicinity of the barrier is the most important quantity for nucleation, for the prediction of nucleation. So it's a thermodynamic quantity, right? It contains the nucleation energy. And then we have the beta star, which is a quantity that is related to diffusion coefficients. And that's more or less a transport coefficient. How fast can atoms or molecules be transported within the volume? I want to go into more details because the equation that I was showing you is the steady state nucleation rate. And that means that's the nucleation rate that you can observe once the system has come into some kind of equilibrium steady state. And this equilibrium or steady state is meant in terms of the number of clusters of various size. So I have plotted the cluster density as a function of cluster size, just a sketch of it. And what you usually observe is that if you have a system which is not supersaturated, so it's let's say undersaturated, then you have a certain distribution, a stable distribution of clusters of various size. So the most of the clusters will be monomers, and the larger the cluster is, the less number of these clusters exist. And following nucleation theory, the nucleation rate is can be defined as the number of clusters of exactly critical size passing to critical size +1. And once you keep that in mind, that nucleation is more or less the number of clusters that will come over the critical size, the flux of clusters in cluster space. Then you can think about, okay, is this distribution that is a function of temperature, is that always existing or not? And I will give you a simple example. I will consider an annealing process where we have a material and we anneal it at rather high temperature T1. The higher the temperature is, the lower is the number of large clusters, because entropy in the system will more or less destroy everything which becomes too large. So when you now quench the material into the region where nucleation occurs, then the cluster distribution must adapt its equilibrium value, and that will take some time. And this is exactly what people consider as time-dependent nucleation. So at time t is 0, there will be no nucleation yet because the clusters are not yet large enough if you quench from higher temperature. And it would take some time, and this incubation time is related to the time it takes to produce the first clusters of sufficient large size. Frédéric Sanson and Georges Martin, they have made a very nice experiment on the computer where they have annealed a system at high temperature and then quench into the precipitation range, or start with a distribution very close to the phase boundary. You can see the open circles are the number of clusters if you have say the equilibrated system, and the full circles are the ones that show a clear time lag until steady state is reached. So the reference are given if you want to know more about that. So transient nucleation is something that does exist, and you can formulate that in mathematical terms with either of these two functions, 1 minus exponent or the exponent of minus. The tau, the incubation time, is either above or below the correction line. Yeah, and then you multiply the steady state nucleation rate by this some additional function, and then you arrive at the, let's say, the classical nucleation rate expression that we usually use in simulations. So this is the exponent term describing more or less the probability of a single nucleation event, and 0 multiplies that with the potential nucleation sites, how many attempts are there. Z is the thermodynamics of the barrier value, the diffusion coefficients in the beta star, and the transient one. Yeah, and I told you the most important one is G star. And the G star contains interface energy and chemical driving force. And we are going to discuss the possibilities next, how we can predict these two values. Yeah, to be honest, the first value, the D, which is the effective driving force, I will not discuss because that is a thermodynamic quantity, and that you can calculate from computational thermodynamics. Thermocalc, MatCalc, Pandat, whatever you have, Gibbs energy minimizer, a thermodynamic database, you can calculate the chemical driving force. This gamma is the much more interesting part, because that is not so clear yet and not so well established in the community, that gamma is not a fitting quantity and is a quantity that you can really predict from basics. Yeah, how can you do that? You simply go back to the really old great guys. The one who discussed this interface energy calculation first was Richard Becker, 1938, so that's quite a long time ago. And in his paper, he proposed the idea that the interface energy can be calculated from the thought experiment, which is on the screen. Take two phases, alpha 1, alpha 2, cut them in the middle and assemble them with the other part. And then you simply go ahead and say, okay, the energy difference between the left and the right state is simply the interface energy, 2 times the interface energy of the system. And the task is now simply, okay, how can we calculate that? What Becker assumed was, let's take a sharp interface. This is 2 sketches of sharp interfaces. That means the 2 phases are exactly separated by a planar and sharp interface. No atom is on the wrong position. No entropy. And that makes things a little bit easier, because when we can ignore entropy, we just have to count on the bonds. And the suggestion was now, okay, let's count the bonds across the interface, and let's separate them, and let's evaluate the, let's say, broken bonds by this thought experiment. And this has been done by Becker already in the nearest neighbor approach. That means only the bonds which are going to the next nearest neighbors are counted, the rest is ignored. And after bond counting, Becker arrived at an expression that said, okay, the interface energy gamma is related to the number of atoms per interfacial area and the number of broken bonds, so a structural factor, and then the binding energy between the atoms, the atoms between A and B, AA and BB. And Becker was a physicist, and that meant for him the problem is solved for him. So he didn't go further because this equation is complete. The only problem is that we don't know anything about the epsilons. Yeah, so we have a nice formula, but we cannot evaluate it because we don't know the binding energies between the atoms. It took a few decades more until David Turnbull suggested that this nasty term with the epsilons can actually be replaced by a thermodynamic quantity. What he did, he was using the same bond counting strategy to evaluate the enthalpy of solution, delta H sol. And he ended up with an expression that is also a structural factor. This is avocado number and coordination number, and the same nasty term in terms of the binding energies. Now, when you take these two equations, you can get rid of the epsilon parts, and you can end up with a description where the interface energy is only related to the enthalpy of solution. And that we do know from Kalfat databases, from computational thermodynamics. So that was in 1955. And when I was working on that topic, I found out that hardly anybody in the community was using this equation. I came across one paper from Nigel Saunders, who used this equation as it is in nickel-based alloys with good success. I was using myself the same equation also for BCC system, and the predictions totally failed. So what we did was we thought about, okay, what could be the problem in this equation? Why is it giving incorrect predictions, particularly in BCC systems? And that was a cooperation that I had with Bernhard Sonderegger for many years, where we developed the generalized broken bond model with the simple idea of saying, okay, maybe the next nearest neighbors are not sufficient interactions to count. So what we did was we went into some kind of numerical scheme, and we said, okay, we will count all bonds across the interface and infinitely large into the volume. And we replaced the number of broken bonds by effective numbers and effective coordination numbers. And what we did was simply saying, okay, we have an energy for the first nearest neighbor, and the second, third, and fourth nearest neighbor will have a decreasing interaction energy with some kind of function. We actually used the Lennard-Jones potential, so 1 over r to the power of 6. And with that, we could find some convergence. When you go ahead and when you integrate that over 500 nearest neighbor shells, then you converge. And by that, we could also show that it's necessary to take into account farther interactions. And the result was that for different directions, we got a structural factor that was in the vicinity of 0.32 for FCC, for BCC. And when you look at the table where we made some orientation dependent calculations and then formed a mean value, we could find very close together numbers for FCC and BCC. And this is actually the value for the structural factor that we are using now in all the computations that we do. So the planar sharp interface model in the generalized broken bond approach does give you reasonable predictions now with good accuracy, also for BCC and for FCC. Yeah, the next thing that we observed was once the nucleus becomes rather small, then our predictions are also not so good as we wanted it to be. And what we realized quickly was that if you have a curved surface, like a small precipitate with a highly curved surface, then the number of bonds that go across the boundary are much less compared to the planar interface. And we worked on that and came up with an analytical expression for the effect of size on the interface energy. So I'm not going into too much detail. It's an analytical expression. So it's this factor alpha as a function of the radius. And that's normalized with respect to the nearest neighbor distance. You can see that once the particle becomes smaller, the effect becomes incredibly large for the interface energy. Because keep in mind, the interface energy is cubed in the nucleation barrier, and it's in the exponent of the nucleation rate expression. So the factor here, like 20–30%, doesn't sound very spectacular, but you cube it and then you put it in the exponent, and then you have tremendous impact. So this is the size effect. Becomes very strong once the nucleus becomes smaller. There's another effect that we had to take into account, and that's the diffuse interface effect. That's an effect that takes into account that the interface is hardly ever really sharp. So there's always some atoms which are on the wrong side of the interface, and that will produce entropy. And this entropy contribution can be substantial if the precipitates, if the nuclei are, let's say, weakly bonded. So we set up a model for the diffuse interface. We started with a sharp interface, which was more or less this sharp gradient, and then we introduced layers. And within these layers, we could calculate the mixing of atoms. We could calculate some concentration profile in the interface. And from that, we could calculate also the energy change that's related to the interface energy. Unfortunately, the solution is no longer a closed form, but it's an implicit equation. In the most simple case, usually you have to solve the problem numerically. The one approximation that we published also in this paper is the one where we said, okay, let's assume simple regular solution thermodynamics and only one intermediate layer. And for that, we could actually solve the problem. And we could solve the problem in terms of the so-called regular solution critical temperature, which is the highest temperature that you observe for a phase separation in the middle of the dome of the phase diagram. And what you could see, or what you can see here in this graph, is that there's also some kind of a factor which decreases the energy. Let's say if you start at the unit value here, then you can see with increasing temperature, the driving force goes down, and it goes to 0 once you reach the critical regular solution critical temperature. And the comparison with other approaches that are published in literature have given us very, very nice, let's say, confidence that the approximate solution is not too bad. And we are using that on a regular basis now. And that was more or less the part that we developed in the last years, and that we are using on a regular basis. Let's go now ahead and look at two examples. The first one was a problem that I encountered many years ago when I dealt with the iron copper system, precipitation of copper particles in ferritic iron matrix. And the problem is very simple. It is related to the question, okay, what is the exact chemical composition of the nucleus when it forms coherently in BCC, in the BCC matrix? Because the copper phase is actually a solution phase, so it can contain more or less iron atoms also, And in fact, it can span the entire compositional range from 100% iron to 100% copper. The problem that I encountered is here on the screen. When you have two phases in the Gibbs energy composition diagram, yeah, like this is the alpha matrix, and this would be the precipitate. And if the precipitate has a certain range of chemical compositions where it exists, then you always need to calculate chemical driving forces. I'm not going into the basic lecture now how to do it. It's this extrapolation here and then this difference. So actually all the chemical potential extrapolations, everything which is below this line is a thermodynamic stable chemical composition, and there could be a particle of any of these compositions forming. So the question is, which one is the most successful one? The classical one is to assume that the particle has the highest chemical driving force. That is the parallel tangent construction. Once you do that for the iron copper system, you arrive at the Gibbs energy diagram that looks like this one here. So you have a very low solubility range in the edge, on the edges of the system. So 1 or 2% solubility on either side, and all the mixtures in between are not favorable. So you will have, in equilibrium, you will always have a complete decomposition of iron-rich particles and copper-rich particles. But computational thermodynamics does allow us to still evaluate the driving force for any composition that we can imagine. And this is done here on the right diagram. So I made the calculation for the chemical driving force as a function of the copper content of the nucleus. Yeah, and you will find that at 500 Celsius with 2% copper, that the copper precipitate can become stable at higher copper content than 0.3 something. And that's an interesting observation, because that means that all of those compositions here have a positive driving force. So what will be the one that is observed in reality, in nature? The assumption that I made was the following. I said, okay, why not assume that the composition will be such that the nucleation barrier is a minimum? That sounds very plausible, yeah? The one where the nucleation barrier is a minimum is the one where there should be the highest probability of a nucleus forming. So the next problem was simply, how can I calculate the nucleation barrier from my knowledge? So what I need is, I need information on the surface energy, on gamma, and I need information on the driving force. The driving force I was already showing you. This is a function for the driving force as a function of nucleus composition. And this is now the interface energy calculated as a function of the composition of the nucleus. And that is also something that you can see is increasing with the copper content of the particle. So basically, theory gives you the approximation that the interface energy should be proportional to the square of the copper content difference between matrix and particle. Yeah, when you have the two functions, you can put them into the equation and calculate the nucleation barrier, G star. And this is what comes out. This is the copper content. And you can see that the function has a minimum here in the proximity of half and half copper and iron. Okay, now you can say, yeah, but this is not very much. Yeah, so it's 20 kBT and the other one is 40. It doesn't make a difference. It does make a difference. Once you put that into the exponent, yeah, you can see that the probability of nucleation becomes very sharp around this 0.5. So the theoretical prediction was that the copper nucleus will contain roughly half iron. Yeah, it's an ongoing discussion that I will not open here. Yeah, there's experiments showing the one and experiments showing the other extreme. At present, I think we are pretty much in agreement that the nucleus will really have a lot of iron atoms incorporated, but as soon as the copper particle grows, it will kick out the iron immediately. So that's sufficient for this particle. And now comes the reason why I have gladly accepted this short-term invitation to give the presentation, because I was working on some data that was published by the group of Benjamin Milkereit. He was doing continuous cooling DSC experiments in the 6000 aluminium system. What you can see here is the DSC signal, the experimental points. The DSC signal as a function of the cooling rate. So there's a lot of variation in the cooling rates. And I'm particularly interested now in this slow cooling region. Because when you look at the system here, when the alloy is cooled, the DSC signal comes up roughly at 500 Celsius. So I said, okay, I dealt a lot with nucleation theory, lots of things that I did. So it should be possible to reproduce the experiments. And with everything that I told you so far, it was not possible to get any of these data reproduced. So focus on the roughly 500 degrees where apparently magnesium 2 silicon beta phase will precipitate. So when you look at the driving force as a function of temperature, this is the chemical driving force in kilojoules per mole. Roughly at 500, you can see that the driving force is extremely low. It's roughly 2 kilojoules per mole. That will give a nucleation barrier of roughly 3000 kBt. And for 3000 kBt, remember that you have to put the value of 3000 in the exponent and make a minus. So e to the power of minus 3000. Your pocket calculator will have an underflow, so it's practically 0. So there will be no nucleation if you simply use all the ingredients that I was proposing so far. But what I realized, or what we realized in analysis of the data, was that nucleation of this Mg2Si phase occurred on the dislocations. And to be honest, it occurred on the, not dislocation, on the grain boundary corners, predominantly at the grain boundary corners. So what we did was simply think, okay, when a phase forms on the grain boundary, like this one here, then the phase will remove this area of the grain boundary, the dark area. And that's an energetic advantage. So we now go ahead and put this energy as a favorable term into our nucleation energy. And here's some proposal for dislocation energies. And here's the proposal for the grain boundary corner. And you can always see this is the energy of the grain boundary, which is a very important ingredient here. So with this knowledge, with this theory, we went into the nucleation rate again. We used the extended classical nucleation theory. That means we consider the volume free energy change is a function of radius. Okay, it's not in the present calculation, but the interface energy is a function of the radius of the particle. It is a function of temperature because we have this diffuse interface effect. And we take into account the heterogeneous site energy that is related to the nucleation site. Yeah, and then I went ahead and calculated the nucleation barrier at 500 Celsius. And this is the 3000 kBt, which I was indicating before. Yeah, the red line is classical nucleation theory. Yeah, and that will predict this high barrier, which will absolutely avoid any precipitation. Now, what happens if we add, let's say, the temperature effects? So this plus beta means this is the diffuse interface effect. That will reduce substantially already the barrier, but it's still too high. If you add the size effect, it will not help very much because the particle is too large here. It's still critical radius of 4 or 5 nanometers. The heterogeneous site energy of the dislocation could help a little bit, but not too much. But if you look at the grain boundary edge, and grain boundary corner effects, then you realize that these heterogeneous sites can decrease the energy so much that nucleation will be possible now, also at the very high temperature, in accordance with experiment. And this is a close-up, and the next diagram shows an even higher close-up. The variation in the barrier is now only in the temperature. And it's only for the barrier at grain boundary corners. There you can see that with decreasing temperature, grain boundary corner energy will become negative. This is a close-up for 512 Celsius, where you can see that the nucleation energy goes down immediately. But please ignore this shaded area because that's outside of the validity of one of the models. So start at nucleation radius of 0.4 nanometers, which is probably 4, 5, 6 atoms large. For that, you can see that nucleation barrier goes down, and then you have a little hump. Still, you're negative in value, but the nucleation barrier must still be overcome. So this is the G star for 512. Even if all the values are negative, you have to count this barrier here. But if you go to 508, you will find that the barrier will totally or completely disappear. And that is something that solved the problem of how nucleation of this atom or of this phase can occur, even in very slow cooling, in very low supersaturation regime. Yeah, the analysis on the next is also interesting. So I was calculating the nucleation barrier as a function of temperature for different heterogeneous sites and for different values of the grain boundary energy. So this nucleation, this heterogeneous nucleation is apparently also a very strong function of this heterogeneous site energies. And when you go into literature and look for grain boundary energies for aluminum alloys, you will find values straight away between 0.3 and 0.6. And this diagram is simply showing you the consequence. It's dramatic. So if we have high grain boundary energy values, the nucleation barrier will disappear at grain boundary corners already at 512. If we have smaller values for the grain boundary energy, the nucleation can be suppressed even down to 460, 470. Yeah, but basically it solved the problem. Yeah, it's now clear for us why the Mg2Si phase can nucleate. Also, with classical nucleation theory, one could never observe any of this precipitation below 400 degrees. Yeah, the purpose of the lecture was to summarize a little bit what we know about nucleation of second phases in metallic microstructures. So I was showing you classical nucleation theory, which comes from the textbooks and which is very basic and very handy theory, giving really good predictions in terms of how much supersaturation or how much undercooling do you need to make nucleation possible. But if you go into metallic microstructures, you need to take into account at least the interface energy size effect, the diffuse interface effect. You have to take into account coherency stresses. Yeah, so there's One example that we published many years ago for the aluminum nitride precipitation in steel, where we could clearly show that homogeneous nucleation of aluminum nitrides in the crystal is practically impossible. And you need very high supersaturation to nucleate on these locations. And that was possible by the proper prediction of the coherency energy of this coherency stress elastic misfit energy. What was new, and what's not so much published, or what's not so well known in the community is how to take into account the nucleation site energies of grain boundaries or grain boundary corners. So we are going to publish that soon, and yeah, let's see what the referees say. Yeah, and I've also showed you a suitable model that can predict the chemical composition of the nucleus of solution phases. That was on the example of the iron copper system. And my experience with all these investigations, with all that research now, is that if you take that all into account, I think we can get into very good quantitative agreement also with what is found experimentally. Thank you very much. That's all I wanted to tell you.
All right. Thank you very much, Ernst, for this very inspiring lecture. And yeah, maybe on the most important topic in physical metallurgy. And nucleation, as you have shown, determines so many processes in materials, and at the same time, it's such a difficult parameter to grasp. Yeah, it's really important to understand it very well, and I think you have explained it into great detail for a very broad audience. I counted more than 200 participants, so you have inspired today 200 people. Thank you very much for that. With that, I would actually like to open this presentation for discussion.